In Lesson 8, we solved the short dipole by treating the current as uniform along the wire. That uniform current assumption made the integral trivial and gave us the sine theta pattern. But a real antenna that is not electrically tiny cannot carry a constant current from feed to tip. The current must go to zero at the open ends of the wire. So the first upgrade is to replace the uniform current with a realistic distribution. On a center-fed dipole of total length L, the current follows a standing wave shape. It peaks at the feed point and drops to zero at each tip. For a half-wave dipole, where the total length equals lambda over 2, the distribution is I0 times cosine of kz prime. This cosine profile is the key difference from the short dipole. Now, the radiation integral no longer collapses to a constant times the wire length. The cosine current must stay inside the integral and shape the final pattern. Place the half-wave dipole symmetrically on the z-axis, running from minus lambda over 4 to plus lambda over 4. The far-field vector potential integral now reads: the same 1 over r factor comes outside, but the integrand carries I0 cosine of kz prime times the source-dependent phase. Unlike the short dipole, we cannot pull the current outside because it varies along the wire. We evaluate the integral directly, and the result is a new pattern function. After evaluating the integral, the far field of the half-wave dipole becomes E theta proportional to cosine of pi over 2 times cosine theta divided by sine theta times the usual 1 over r decay. Compare this with the short dipole's pure sine theta. Both patterns are 0 on the axis and maximum at broadside, but the half-wave pattern is slightly narrower. The extra cosine numerator squeezes the main lobe inward, concentrating slightly more power toward the equator. In 3 dimensions, this narrower pattern still looks like a donut around the dipole axis, but it is a thinner donut than the short dipole produces. The null along the wire axis remains. That is a fundamental feature of any linear dipole. The broadside maximum is still the strongest direction. What has changed is that the half-wave dipole pushes a little more energy toward broadside, making it a slightly better radiator in the equatorial plane. The half-wave dipole gives us 2 numbers that every antenna engineer memorizes. The directivity is 1.64, or about 2.15 dBi, and the radiation resistance at the feed point is approximately 73 ohms. That 73 ohm value is remarkably close to standard transmission line impedances of 50 and 75 ohms. This near match is the practical reason why the half-wave dipole became the universal reference antenna. Almost every antenna gain specification you encounter is measured relative to this dipole. The half-wave dipole upgrades the short dipole in 3 ways. First, the current distribution changes from uniform to cosine, reflecting the standing wave on a real wire. Second, the radiation pattern narrows from sine theta to the cosine over sine function, giving slightly higher directivity. Third, the radiation resistance of 73 ohms makes impedance matching straightforward, which is why this antenna became the standard reference. So far, every antenna we have studied is a single element. The next natural step is to ask what happens when we combine multiple dipoles into an array. That combination introduces a new degree of freedom. The spacing and phasing between elements can steer the beam electronically without moving the antenna. That is the doorway to array theory.